Alright, so now we know how to calculate the zero input response for a differential equation, or for a linear time invariant system described by a differential equation, assuming that the characteristic roots are real and distinct. Now let's discuss a couple of other cases. The first case will be, what if we have repeated roots? When we have repeated roots, let's say the repeated roots is lambda. And it's repeated several times. Then in addition to the common characteristic mode, e to the lambda t, right? This is what we discussed. Since you have to also take into account the repeated ones. If it repeated twice, you should have two characteristic modes. If repeated 3 times, you should have 3 characteristic modes, corresponds to the same lambda. And to accommodate that, mathematically it can be shown that in addition to e to the lambda t, e to the lambda t times e to the lambda t, t squared e to the lambda t, and so on can all be a possible characteristic modes. If it's a distinct single root, we only have this one. If it's repeated once, meaning you have a pair of repeated roots, then you have 2 of them. If it's repeated 3 times, then you continue with 3 of them. And this is the only difference compared to the others. You're still gonna, assign the C1 and C2 to them, but taking the derivative of these ones will require a slightly more complicated procedure compared to the single one. Again, we'll use an example to illustrate how this works. And this example is as follows. Plus 4 dy dt plus 4y equal to 3f. And let's say the initial conditions are y0 equal to 1 and dy dt at t equal to 0 minus is equal to 3. And I still want to know what is the zero input response. The entire procedure is almost exactly the same. The only difference is how we find the characteristic roots. So we'll follow the same procedure as the previous example. The first step, characteristic equation. Will be lambda square, corresponds to the second derivative, second order derivative, and then 4 lambda, the second term, plus 4, the constant term corresponds to the opposite itself, equal to 0. Okay. For the characteristic equation, we don't really have to care about the right-hand side or the input signal side, only the output signal side. Second, solve for the roots. In this case, we can easily find out this is lambda 2 square equal to 0, or in other words, lambda will be -2, -2, right? We have repeated roots. And when it appears twice, the third step will come to us writing this general form of the zero input response by plugging in the characteristic modes. So y of t will be equal to c1 times one of the characteristic modes plus c2 times the other characteristic mode. Since you have quadratic equation, 2 characteristic modes are needed, and the first one will be e to the lambda 1t, so e to the -2t. And the second, as I mentioned earlier, we have to take this into account. So times t e to the negative 2t. And that's it. This is the only difference. Okay. Then step number 4, initial conditions will be plugged in. So 0 will be equal to c1 times e to the 0 as usual, so I don't have to write it down again. Plus, the second term is even simpler because when t is equal to 0, c2 times 0 will be 0. So, right, so it will be c1 plus 0 equal to the initial condition. Let's see what it is. It's equal to 1. So it's equal to 1. The derivative terms can be slightly complicated, right? But it's not indeed that complicated because of this t involved. So when you do that, you will find out the following. Well, the first term still is going to be negative 2 times c1. And for the second term, we can do it a little bit slowly. Right, c2 is a constant, you can pull it out. And then do the derivative inside, and you have done this in your single variable calculus class. It will be 1 times e to the negative 2t. That's when you take the derivative with respect to the first term, plus t times negative 2 e to the negative 2t. So second term is when I take the derivative with respect to t on the second term, e to the negative 2t. And this will be evaluated at e at 0. Okay. What is it equal to? Negative 2c1 still have to be there. And 0 plug into the second, I have c2. 0 plug in the second, since there's a t here, t will be substituted by 0, so the second term will be 0. So that's what we have. And then we plug in the initial condition here, equal to 3. Now, in the first equation, you already have c1 equal to 1. And with the second condition, you have c2 equal to 3 plus 2c1, in this case will be equal to 5. And you have solved this equation. Just have to summarize your result together. And this will give you c1 equal to 1, so e to the negative 2t. And then c2 equal to 5, so 5 plus 5t e to the negative 2t. And you can say this t is greater than or equal to 0. That's the 0 input response. And for the repeated roots, it's pretty simple. The only variation, as you can see, is how to deal with the repeated roots. How to add the more characteristic node that correspond to the same root. And the rest of the procedure is relatively straightforward. Okay. This is the case where we have repeated roots. A more complex and more challenging case is, what if there are complex roots? Now let's assume the complex roots are not repeated in this case, but when you have a complex roots, from your algebra knowledge, you should know that if one root is complex, alpha plus j beta, for instance, its complex conjugate also must appear as the root to the same equation. Right? This is a given result, so keep in mind if one of them is a root, its complex conjugate must also appear. They have to appear in pairs. And the definition of complex conjugate is the two have to share the same real part, alpha, and the imaginary part will have opposite sign. One is beta, the other is negative beta. Now let's assume we're dealing with a simple case quadratic equation, just a pair of complex roots here, then the zero input response. When you have this pair of complex roots, will be what? They're still different, they're complex, but they're still distinct, so I can still apply the same rationale to put together these two characteristic modes, right? e to the lambda 1, t to the lambda 2, t. Only here, this lambda 1 and lambda 2 are complex numbers, but we have discussed in chapter 1 how do we deal with exponential signals where the exponent lambda or alpha or a is a complex number. So if you have forgot, you want to go back and check your notes. And how do we deal with it? We plug in lambda 1, lambda 2 with alpha beta, and you'll find out this with c1 e to the alpha t times e to the j beta t plus c2 e to the alpha t times e to the negative j beta t. So that's how we plug them in. Now, the way to proceed is that we can apply Euler's formula to both of these complex terms, and that will do what? That will do the following. This will be cosine beta t plus j sine beta t plus c2 times e to the alpha t cosine beta t minus j sine beta t. So this is the implication of the fact that the sinusoidal sine of t or sine of x is an odd function, so we can flip the sign. And again, this is just another way of the Euler's formula. Now, remember I'm talking about the response. The response is the physical signal of a system, no matter if it's electrical, mechanical, or thermal, or anything else. It's the signal physically has to be something that only takes real values, cannot have any complex or imaginary part. But if that's the case, right, seeing here with the j's, they have to be able to cancel each other, right? Or in other words, so this means since signal is real. When I say the signal, I mean the zero input response. This means the imaginary part I'm looking at here must cancel each other. So c1 e alpha t times j sine beta must be equal to c2. Sorry, let me backtrack. Since they must be real, right? C1, C2 must be able to quote unquote cancel all the imaginary parts. Okay. You have this two being imaginary, but also I didn't say anything about C1, C2, so you should keep in mind C1, C2 may be complex numbers too. They may be complex numbers. There's no assumption that C1, C2 has to be real. So when you have a pair of numbers, one's like this, the other's like this, and they look so similar, right? They look so similar. And if you want to make sure that when you add these two signals, or these two parts, the eventual signal is always real, always take real numbers, reals, just real. It can be shown mathematically that this requires C1 and C2 be complex conjugates. They must be a pair of complex conjugates. Okay. The proof can be done by writing C1, C2 in terms of another pair of complex numbers, and you can plug in the equation, and if you want the imaginary part to cancel each other eventually for all t, and you will be able to prove this as well. But since this is the case, I will directly use this result. I'll assume, since they're complex conjugates, C1 will be equal to C over 2 times e to the j theta, and C2 will be equal to C over 2 times e negative j theta. Okay? And without loss of generality, I can assume C is a positive number, for instance. But if C is a negative, it doesn't really hurt. But since I use it, you can see I put the complex numbers in the polar form, I'll take this. And you may ask why we have C over 2 instead of C. Well, we use C over 2 such that the subsequent derivations can be more straightforward. And proceed with that, we'll find the zero input response. Enter this result can be written as C over 2 times E alpha t times E. Now, although I can use the two terms in the blue box, what I'm really going to use is these ones. I'm going to use this line, because I have exponential signals multiplying with each other. And I have e to the j theta here, I have e to the j beta t here. I can easily combine them, making e to the beta t plus theta, c over 2, e to the alpha t, and e to the negative j beta t plus theta. Okay. Then what we have? We have c being a constant, a common factor between the two terms, of e to the alpha t being a common factor between the two terms, and then I can put e j beta t plus theta plus e to the negative j beta t plus theta over 2. Now, for this term, you can apply Euler's formula individually. Or if you know a variation of the Euler's formula, it says e to the j, I'll use another another symbol. If you know a variation of the Euler formula, it says this is equal to cosine of phi. Then applying this result, this whole thing can be now written as this. can be written in this form. Now, and always keep in mind we're talking about zero input response, right? And at the beginning, what we did, we utilized the material that we have discussed earlier. We say, well, they have to take this exponential form. Okay. And we know to calculate this C1, C2 before we will apply the initial conditions. But since now you'll be dealing with this complex signals, it may not be that straightforward. So what we just did is another option to look at the zero input response. Instead of expressing it as the sum of two complex exponential signals, and eventually convert it into one signal that is a product of an exponential signal and a sinusoidal signal. Now, alpha, beta are known. They are the real part and imaginary part of your complex truths. The only thing you need to solve will be C and beta and theta. So C and theta left to be solved using initial conditions. Okay, so this is the procedure that we have in when we have complex roots. Let's pause a moment. In the next video, we'll use an example to illustrate, well, how on earth are we going to use the C e to the alpha t cosine beta t plus theta formula to calculate the zero input response for this complex root case.